evening, everyone. Welcome to the Saturday series. Today's topic is about solar energy harvesting. The presentation will describe the different avenues of solar energy harvesting. It will start with the introduction of solar energy to harvest renewable energy and traditional methods of solar energy harvesting. Finally, we will understand the recent trends in harvesting solar power using solar terminals, solar thermoelectric generator, etc. The future of solar energy harvesting depending on the utility of the IoT-based devices will be also discussed. Well, today we have a faculty from Amrita Vidyapeetham, Dr. Sudip Kumar, Associate of Department of Science, Senior Research Scientist at Amrita Center for Industrial Research. So participants, before getting to the sections, if you have any queries, please type it in the chat box. Sudip sir, I welcome you to the session. Therefore, we can start the session. Over to you, sir, right now.
Okay, thank you for the introduction. So I think we can start the session. So I just I can say that we believe that the sun has been worshipped as the life giver to our planet since ancient times. Okay, so I'll share my screen first. I think my screen is visible.
Yes, sir, it's visible.
So from this belief, actually, we believe that all that exists was born from the sun. Am I right? Now, all that exists was born from the sun, because from the school life, we learned the source of all energy is the solar energy. So from this point, actually today's talk is the solar energy harvesting. How we can harvest the energy from the sun. So before starting with the solar energy harvesting, I just want to give a brief introduction from where I harvest my energy for the research. I did my Ph.D. from ISCS, Indian Association for Cultivation of Science. It's in Jadavpur, Calcutta. It is the oldest research institute in Asia. So after completing my Ph.D., I went to Singapore, National University of Singapore. I did my postdoc and I joined as a scientist in Nanyang Technological University. And 2015, I shifted to Amrita, Coimbatore campus. So these are some of the picture of my workplace. This is the Indian Association for Cultivation of Science, from where I did my Ph.D., Jadavpur. And these are the workplace, NUS and NTU. And last, this is my current workplace, Amrita Vidyapeetham, Coimbatore campus. It's a very clean and green campus surrounded by the mountain. So let's start the topics, how we can harvest the energy from the sun. So before going to energy from the sun, I just want to give an introduction how we are now generating the energy. This is the energy generation procedure. We are using the two different sources, non-renewable and the renewable source. If you see this chart, you can see that how we are generating the energy. We are using the oil mostly, then we use the natural gas and the coal. So mostly we are using the fossil fuels. So definitely if we are using that much fossil fuels, in near future everything will be finished very fast. So we have to think to use some renewable source of the energy. These are the renewable source of energy: solar energy, wind energy, biomass energy, tidal energy, small hydropower, and geothermal energy. So I just want to see how much energy come from the sun. So sun is the source of a very big nuclear reactor. Now we have a fusion reactor that have been burning over 4 billion years. This is the sun. But only 0.023% of this energy received by the plant, and they did the photosynthetic process, and that energy is come to us. So this is the source of the all life in the earth. Only 0.023% of energy. Now, whatever the energy is coming from the sun, some of the energy is reflected back from the atmosphere, and whatever the energy reached to us, the surface actually, whatever we received is only 47% of the total solar energy that reaches to the earth. So, is this energy enough for our energy demand? Because we have a lots of demand for the energy. We are getting only 47% of energy, whatever reaching to us, because the rest of the energy is reflected back from the atmosphere. So, let's see how much energy sun is giving to us. So this is the solar energy per year we are getting, 1.56 into 10 to the power 18 kilowatt hour. And how much energy we need yearly? Yearly energy demand worldwide is only 1.1 into 10 to the power 14 kilowatt hour. So the sun provides enough energy in 1 minute to supply the whole year. So if you can harvest the energy coming from the sun in a minute, I think the whole year you can just sleep. No need to harvest any more energy. The amount of solar radiation striking the earth over 3 days period is equivalent to the energy stored in all the fossil energy sources. So whatever the fossil fuel we have stored, if you just harvest the energy for 3 days from the solar energy, I think you no need to touch anything. For the energy will be equivalent to the stored energy. The amount of the solar radiation striking to Earth a day, that can be used by the whole 7 billion human in 27 years. So hold the energy, if you can harvest 27 years, you no need to harvest any more energy. The worldwide energy demand is only 0.01% of the energy introduced by the sun. So however the energy you are getting, if you can just harvest 0.01%, that is enough for our energy demand. So whatever about India, in India we are getting a sufficient energy from the sun, yes, with about 300 clean sunny days in a year, and most part of the map you can see we are getting the radiation. This part radiation is very good near the Rajasthan and Gujarat, and that way you can understand how most of the solar plants, power plants are, and the solar thermal plants are situated there. I think in the southern part also we have a very good radiation. So there is a very bright future for harvesting solar energy for our country also, and we are now going to that direction. So there are two different ways we can harvest the solar energy. One is called the solar thermal, another is the solar photovoltaics. Solar thermal is just the heating by using the solar energy. We can use the heat water for cooking or for the room heating, whatever the needed. And solar PV is the direct electricity production from the sun. I'll come one by one. Let's discuss first about the solar thermal technology. Solar thermal is very clean and highly.
আমাদের ঢোকার দরকার নেই, আমিও ভাবছি বেরিয়ে যাব।
Sorry.
Sorry,
Someone muted,
Okay.
please.
দেবদাস Batabyal।
না আমাকে পাঠিয়ে দিতে।
Hello, can you hear me now?
Yes, you are audible.
I think you can mute all the microphone. Yes. Solar thermal is a clean and high efficient means using the renewable energy from the sun, and it's provide the hot water from the domestic, commercial and industrial process. So we can generate the hot water, and that hot water we can use for domestic and the industrial process. And it's nothing but if you keep just one bucket of water in your garden, you can see that water will become hot. So this simple method you can do by little bit applying some technology. So this is the solar water heater. So this box, we have some spiral pipe. You see the cool water is coming in here, and we have make it is a spiral, so it can absorb the maximum amount of the solar radiation. So after absorbing the solar radiation, water become hot, and from the outlet we are getting the hot water. So there are different type of the solar thermal collector. We can make a flat funnel collector, so water is coming from the top to down, and in the time of movement they can become hot. We can make a evacuated tubular solar collector. So what is the advantage of evacuated tubular collector? Whatever the energy going inside, so this is a double wall glass pipe. So in between the two wall you have evacuation, so it will be non-conducting of heat. So whatever the energy is going inside, they will not come out. The working principle is quite similar like a thermoflux. I think you know the thermoflux. No? If you put the hot water, water will be hot, I think for a long time, near about 10 to 20 hours water will be hot, because in between, in the thermoflux we have a double wall glass bottles. So in between the two wall there will be vacuum, so heat cannot come out. So we can use the same technology for the solar thermal collector also. So whatever the heat going in, it will not coming out. So we can get a very good efficiency for the solar thermal collector. And next application of the solar thermal energy is the solar cooker. We can use the heat energy coming from the sun to cooking. So we can make this type of box. You can see, I think this picture, there is a reflector. Whatever the radiation coming from the sun is reflected inside the box. And inside the box, we can put some black color to absorb all the radiation and trap the radiation. And in the top, we can put some glass plate, just like a greenhouse effect. So radiation, whatever is going in, they can trap inside, and we can cook. And the main advantage for solar cooker, this cooking is very low temperature cooking, and the nutrient values will be maintained. So these are the time taken for the cooking in this type of box type of solar cooker. If you want to cook a vegetable, it will take near about 1.5 hours. Rice also near about 2 hours. These are the meat if you want to cook 1 to 3 hours. So there are some disadvantage. It will take long time because the radiation coming from the sun, we have to trap this one, and this is not very high energy. So now day by day there are new and new technologies coming out for making solar cooker also. You can see some of the recent technology. This is called a concentration type technology. So we can use a parabolic reflector, and in the focus we can keep the container. So whatever the radiation coming in this whole area will be focused in a particular point, and it can generate a very big amount of energy, I think 0.6 kilowatt, which can boil 3 to 4 liters of water about half an hour. So within half an hour, we can boil 3 to 4 liters of water. So this type of cooker definitely can cook very fast. Another cooker is recently developed. I think it's also commercially available in the market. It's called the evacuated solar cooking system. I think one of the companies start producing this one, Go Solar or something. It's also quite similar, like just now I discussing about the evacuated solar thermal. So there are also two double jacket glass quartz containers. So in between these two wall, there will be evacuation will be there. So whatever the energy is coming from this reflector to this is the focal tube, they will be trapped inside. So this type of cooker can go very high temperature. So you can do barbecue also. It can go around 300 degrees centigrade inside this tubes. So whatever the radiation going inside, they will be trapped inside. They are not coming out because we have evacuated chamber in between the two quartz jacket. And these are the some of the example of the solar cooker used in India. These are, I think, the Siddhi Sai Baba temple. They actually installed this a big cooking system, the solar cooking system. They can serve 20,000 devotees daily. It has a large 43 parabolic mirrors. So whatever just now we are saying here, that this type of parabolic mirror, they installed their 43 parabolic mirrors, so that can generate huge amount of boiled water. So that boiled water can use for the cooking. So it will reduce the usage of the LPG. So another use of the solar energy, especially this thermal energy, is the solar thermal power generation. This is nothing but we can, the thermal power generation. Now we can generate the steam by cooking by coal or fossil fuels like petroleum gas. So we have to generate the steam, and the steam can rotate the turbine to generate the electricity. But for solar thermal power generation, we actually generate the steam from the solar thermal power. So we can put a lots of reflector, just like a football ground. We can put lots of reflector, and all the reflector focus on a particular point. So in this particular focal point, we can generate a huge temperature. That temperature can be used to generate the steam. So we can generate a huge amount of steam. So pressurized steam can rotate the turbine, and after turbine rotation, we can generate the normal electricity and we can put it in the grid. This technology is known as the solar thermal power generation, and this is the real picture of a solar thermal power generation. I think that focal point temperature can go more than 1000 degrees centigrade. So instead of steam, we can use actually the molten salt. Some salt we can use, which can melt and can convey the heat energy to the source to generate a lots of amount of the steam. These are some Indian picture. I think in Rajasthan or Gujarat there will be some solar thermal power plant. So that's also generate, I think, 177.5 megawatt is in Rajasthan. And in our lab, actually, we are doing some different direction of this using the solar thermal energy. So we are developing some solar thermal evaporation system. So water can evaporate if you keep it outside because of the thermal energy from the sun. So how the evaporation rate? The evaporation rate is very slow. So if you keep just one cup of water, I think whole day also it will not evaporate. So the evaporation process actually takes place from the surface of the water. But if you keep it in the solar energy or in the solar radiation is go inside the water and it actually increase the temperature of the whole water. So what we are thinking, we can trap the solar radiation on the top surface of the water. So whatever the solar radiation coming, they will be trapped on the top surface and the evaporation is happening from the top surface. So we use some nanoporous carbon materials and we float on the top of the water. So carbon actually absorb all the solar radiation, and they have a very nano size or micro size pores. So what are actually coming on these pores, they actually taking this radiation. There will be transfer of the radiation from the nanostructure to the water, and water vapor can generate. So you can see this nanoporous cake actually generated from the potato. And we also generate some nanoporous banana pseudostem. We are using the banana stem. So we are using the banana stem have lots of pores. So using these pores to water to come on the top surface, and top surface we are putting some carbon. And you can see all the evaporated water we can collect if you put some condenser on the top of the evaporator. This is a real picture of the condenser of the solar steel. So whatever the water actually evaporate, we can collect that one. Then we can see, we can get some distilled water. So in the laboratory, whatever we are getting, the evaporation rate around 3.18 kg per meter square per hour. And if you don't put any evaporator, it will be very less. It will be around 0.3, 0.4, maximum 0.5, depending on the radiation. And the device showing 100% dye or salt water purification. So if you put a polluted water or the salt water, I think whatever the evaporated water you are collecting, that will be 100% pure. This is the one published paper. We use the banana stem. On the top of the banana stem, we have put the carbon, and this carbon actually used as a solar energy harvester. So they actually harvesting the solar energy and they transfer the thermal energy to the water for the water evaporation. And you can see this is the collector where we are collecting the condensed water. This is the real picture of the solar steel where we are using this type of banana stem as the solar evaporator. Now let's come to the solar PV. Solar PV is the direct photovoltaic generation from the solar energy. So we are generating the electricity by using the solar energy. So if you see the name, the PV is the photovoltaic, it's converting the light to the electricity. How this PV device actually works? So if we put some solar light to this device, they will generate some charge carrier, electrons and hole. Now if we can collect the electrons and hole in the two different electrodes, you can get a electricity, you can generate the current. So solar cell is a solid state electrical device that converts the solar energy directly into electricity by the photovoltaic effect. So there will be three basic steps. First one is the light absorption. They have to absorb the light. So photon have to go inside the material. Then the photon actually transfers the charge to the electron. So there will be electron and hole pair actually generate. So free charge carrier actually generate inside this material. And now we have to transport this free charge carrier so we can get the current from the device. I will go to more details how this solar PV actually works. So if you want to go inside, you have to get some idea about the semiconductor. We know that silicon is a semiconductor. No? Any material we can classify as a conductor, semiconductor and insulator depending on the Venn diagram. Insulator means they have a very large gap between the conduction band and the valence band. And conductor means they have a lots of conduction electrons. Who have the conductor? Because conducting materials who have a lots of suppose, as for example, suppose silver, gold, aluminum, they are all conducting material. Now, if you see their electron distribution structure, in the last orbit they have a one electron, and below this one they have a lots of electron actually sealed in the nucleus. So the last single electron have a very quick interaction with the nucleus. So whatever the thermal energy they are getting because of the room temperature, they get free and they come out from the atoms and they become a free electrons. So they can take part in the conduction. That's why they are known as the conductor. An insulator, all the electrons are very tightly bound to the nucleus, so they cannot get free. So they don't have any free charge carrier to electricity conduction. But semiconductor is in between the conductor and the insulator. So they have some electrons loosely bound to the nucleus. So especially if you see the example for silicon, silicon have a 4 electron in the last orbital. So they actually share this 4 electron to the 4th side of the another 4 silicon and they fill up the octet rule and they share this 4 electrons. So every silicon is getting the 8 electron. Now the binding energy of this electron is quite weak. So because of this thermal energy in the room temperature, they get some energy and this electron can come out from the orbit and they become a free electron. So when the electron is come out from the orbital, they generate a hole. So this is called the electron hole pair generation. So all the semiconductor, if you give some energy, they can generate this electron and hole pair. Now we can make it two different type of semiconductor, P-type semiconductor and N-type semiconductor. How? Because whatever the silicon you are adding here, if you replace this silicon with a pentavalent material which have a 5 electron on the last orbital, it can share the 4 electron with the 4 side and 1 electron become extra. So this electron can come out. So it's all the dopant material will give one extra electron. So this type of material is known as the N-type semiconductor because they have lots of negative charge, lots of free electrons. And instead of pentavalent, if you incorporate trivalent, it will generate a hole, means it have a vacancy of electrons. So one electron from the outside, they can come to fill up to make the 8 electrons. So they can generate the hole, so a positive charge. So that way they're known as a P-type semiconductor. Now if you can make a joint, if you can make a junction between this P-type and N-type semiconductor, N-type semiconductor have lots of electrons, P-type semiconductor have lots of holes. So in near the junction, they will recombine. And if you see the structure here, when you make an N-type semiconductor, you putting a pentavalent dopant. So they have a 5 electron in the last orbit. If this become free, they have one extra proton in the nucleus. Similarly, for the P-type semiconductor, whenever a vacancy is created and one electron is coming in this vacancy, they have one extra negative charge. So these charges are not moving, and these are known as the immobile charges. So whenever you make a p-n junction, the n-type side have a immobile positive ions. So this positive charge in the nucleus, and the p-type materials have immobile negative ions. This is the extra electron sitting on their orbital, because number of electron and proton is same. But whenever you have extra electrons in this trivalent dopant, you have a charge, extra negative charge there. So this positive and negative charge near the junction of the p-n junction, they generate an electric field. We know that p-n junction diode, the electric field is known as the depletion potential. So in solar cell, this depletion potential actually responsible for separate the charge, photo-generated charge carrier. So if you see the IV characteristics of the p-n junction, I think people know in forward bias it's giving very high current, and reverse bias it's not giving current because of this depletion potential, depletion layer. The charge cannot cross in the reverse bias direction, but we are getting very low current in the reverse bias direction. This is known as the leakage current, and it's generated because of the minority charge carrier. Because though your semiconductor is the p-type and n-type, so n-type semiconductor have lots of electrons, but it's made up with the silicon. So this silicon can generate some electron hole pair. So n-type semiconductor also have very minimum amount of hole. Similarly, the p-type semiconductor also have very minimum amount of electrons. These are the minority charge carriers, and because of this minority charge carrier, we are getting some leakage current in the reverse bias condition. Now, if you give some light to this type of p-n junction diode, we are generating more electron and hole pair. So the electrons in the p-type side is a minority charge carrier, holes in the n-type side is the minority charge carrier. So what actually we are doing? We are actually enhancing this leakage current too much by photo-generated charge carrier. So this IV actually changing. So if you give some extra light, this IV actually changing, this IV actually shift this direction, because this leakage current, whatever we are getting for the minority charge carrier, that actually enhance. So that current actually go down, means we are getting some extra current because of the photo-generated charge carrier, and this is called the short circuit current, and this is called the open circuit voltage. I am coming later. So what is the working principle of the p-n junction? If you give some light, this electron hole pair will be generated. Now all the holes will come to the p-type side because of the depletion potential, and the electrons will come to the n-type side. And if you can collect these electrons and hole from the p-type and n-type semiconductor, you can generate the current. This is the working principle of the solar cell. So we have a p-type material and n-type material. You are giving some photon actually give the energy to the electrons, so there will be electron hole pair will be generated. Now electron go to the n-type side and hole go to the p-type side. So whatever the p-n junction diode we are getting, the IV characteristics, it will be shifted because of the photo-generated charge carrier, and this will give you some extra current and voltage. This is the working principle of the solar cell. And we can normally in the solar cell IV characteristics, we are putting this one in the positive axis to show, because current direction you can change anytime. So if you can see whenever the IV actually crossing the current axis, this is known as the short circuit current. So without any voltage, we are getting some current, and similarly without any current, we are getting the voltage when it is crossing the voltage axis. So this is called the open circuit voltage and the short circuit current. And if you want to calculate how much power we are getting from the solar cell, we have to multiply the current and the voltage. So if you see how much current we are getting a maximum current here, and then the current slowly going down. So though the current is maximum, but voltage is zero, so our power is zero. Also for this point, our power is zero, but slowly power is increasing when our current is decreasing and voltage is increasing. So this black curve is known as the power curve. If you want to calculate the efficiency of the solar cells, this is the efficiency of the solar cells. So how much power we are getting from the solar cell and how much power we are giving the solar cell, this ratio is known as the efficiency of the solar cell. So, okay, just a minute. Okay, so the efficiency is the maximum power point, maximum current of the power. And so if you see this curve, the power curve, this point is the maximum power we are getting for this current and voltage. So we can get the maximum power current. This is called the maximum power current, and this is called the maximum power voltage. If you multiply this IMP and VMP, we can get the maximum power output. So ratio of this maximum power output divided by the power in, that means how much light you are giving, that ratio is known as the efficiency of the solar cell. So now we can divided that IMP VMP with the short circuit current and open circuit voltage, then this ratio is known as the fill factor. So then we can represent the efficiency it as the fill factor into ISC VOC divided by PA. Because we are dividing that maximum current and voltage by ISC VOC, and again we are multiplying with the SC and VOC. So we just converting that IMP VMP to the fill factor. Fill factor is nothing but the area, how much area actually covered by the maximum power point. So normally if you can make an ideal solar cell, the IB should come by this dotted line. So you should get a fill factor is 100%, but because of there will be some recombination of the photogenerated charge carrier, we cannot collect all the photogenerated charge carrier. So in the real solar cell, the power is little bit less than the ideal case. So how much actually we are getting, this is actually giving the fill factor actually giving that idea. So let's come to the solar cell, how we make a solar cell. If you see all the solar cells available in the market, most of the solar cell is the silicon solar cell. I think 90% of the solar cell market is commercial market is occupied by the silicon solar cells, single crystal silicon solar cell. How we can make a silicon solar cell? We can start with the SiO2. SiO2 is very cheap material, is the quartz. So if the SiO2 is so cheap, then why the silicon solar cell is so expensive? The solar cell is very expensive now, because if solar cell is very cheap, we are not using the electricity, because electricity you have to pay the bill. But solar cell, if you once purchase a solar cell and install in your home, you don't need to pay any bill, because the energy coming from the sun is totally free. So where is the secret? Because the price of the solar cell is quite high. Why the price of the solar cell is high? Still SiO2 is very cheap. We have lots of SiO2 because for making a solar cell, you need a very pure silicon. So first we have to make the silicon from the SiO2. So we have to make some carbon, and you have to heat it very high temperature in furnace. I think more than 1500 degrees centigrade you have to heat it. Then you will get silicon from the silicon dioxide. After getting the silicon, you have to make it an organic compound of silicon. Then you have to distillation it. So after distillation, you will get a very pure silicon, and from this silicon you have to grow a single crystals. So this type of very big single crystal you have to grow. Then you have to cut the single crystals to a silicon wafer. After getting the silicon wafer, you can make a PN junction on the silicon by introducing the pentavalent or trivalent dopant to make the p-type and n-type along the thickness of the silicon, and you can make a PN junction on the silicon wafer, and you can take a back contact to collect the holes, and you can make a front contact to collect the electrons. So this is a real device of the silicon. You can see actual device. This is a single crystal silicon solar cell. This is the polycrystalline silicon solar cell. So there are another type of silicon solar cell is called the amorphous silicon solar cell. They are actually classified depending on how we actually fabricating the solar cells. So whatever I am describing here, if you grow this type of single crystals. So first here actually we are purifying the silicon. We are getting a silicon material here, very purified silicon. Now we are melt this silicon, and again we are growing a single crystals. And instead of growing the single crystals from this silicon, if you can cut the wafer, you will get a polycrystalline silicon. So if you don't go single crystal, polycrystalline silicon also can give you the solar cell. The problem is that polycrystalline have lots of gain boundary, and in gain boundary means photogenerated charge carrier can recombine in this gain boundary. So your efficiency will be a little bit less in the polycrystalline silicon solar cell compared to single crystalline silicon solar cell. And amorphous is much more less compared to both of them. And this is the arrays of the silicon solar cell. So we are this, you can see this is the solar cell, whatever we have fabricated in the laboratory in the small size solar cell, and where we can get 0.5 volt output and current around 5 to 6 ampere. Now if we can array in the series and parallel all these silicon solar cells, you can get a module. In the module level you can increase the voltage 20 to 30 volt, current 5 to 6 ampere, and now all these module you can arrays, and to make a solar array, this can give you a considerable amount of power. You can generate kilowatt power by enhancing the voltage and current both. So why we are using the silicon solar cell? If you see that the construction of silicon solar cell, we are cutting a single crystals in small wafer. So if you are cutting by mechanical cutter, means the thickness of this wafer will be few hundred micrometer. So if we are actually making a solar cell, we are using a huge materials, because now the nanotechnology is developing too much. So we can use very minimum material of silicon to make a solar cell. Is it possible? For silicon it is not possible, because the optical absorption coefficient of silicon is very low. So if you want to absorb all the light falling on the silicon, you need few hundred micrometer silicon. That's why you can see all the silicon solar cell is quite thick. The thickness is quite high, few hundred micrometer. So reduce the material cost. So people are thinking whether we can make a silicon solar cell very thin. So then we need some material which can absorb light in this thin material itself. So people found there are some compound semiconductor where their absorption coefficient is very high, like copper, indium, gallium selenide, copper, indium, gallium sulfide, cadmium telluride. These type of materials can absorb all the light falling on them within 1 micrometer thickness. That means 1000 nanometer thickness, they can absorb all the light. So this actually gives the concept of thin film solar cell. Instead of growing a single crystals or the wafer level multi-crystals, we can grow a very thin film and we can put the light there and we can make a PN junction to make a solar cell. This is called the thin film solar cell, and their structure will be quite similar like that. Suppose you have active layer like CIGS or cadmium telluride, and this is the P-type material, and in the top of that we are putting cadmium sulfide N-type material, very thin layer we are putting. On top of the cadmium sulfide we are putting some transparent layer, so transparent conducting material. So normally we are putting aluminum doped zinc oxide or indium tin oxide. These materials are transparent but they are conducting. So we can collect the electron from there, but light can pass through them. And backside we are putting some metal, mostly we are using the molybdenum to collect the holes. So this is a real cross section of this type of solar cell. You can see the scale bar is in micron scale, so they may be the 1 grain of the CIGS can be thick around 1 micron to 2 micron, and top of the CIGS this thin layer is the cadmium sulfide layer, and top this is the aluminum doped zinc oxide layer, and below is the moly layer. So now how you can grow this type of solar cell? So still we have to rely on the vacuum based system, so we have to give the vapors of the copper, indium, gallium, sulfur, or you can make a CIGS and then you can vaporize. So mostly this type of solar cell people are fabricating from vacuum deposition technique. So if it's vacuum deposition technique, you have to suck out all the air, so you need a system where the vacuum level is very high. If the order of 10 to the -6 to -7 order vacuum we need, and we need some complicated setup to grow this type of crystals. So though we can minimize the material, instead of few hundred micrometer we can use only 1 micrometer, but still the price of this type of solar cell also quite high because of this complicated technology to fabricate this type of solar cell. So only future is that whether we can make some solar cell from solution. This is one of the company who are growing this type of CIGS solar cells, and they are putting all the thin film solar cell. So this is one of the advantage of thin film solar cell. You can make a flexible because the thickness is very less. So this will not break, but silicon wafer is quite thick, 100 micrometer thick. So making the flexible silicon solar cell is quite tough. So for flexible solar cells, the thin film solar cell is the best candidate. So in our lab, we are trying to grow some solar cell from nanocrystals. So whether we can grow some solar cell from solution. So nanocrystals means they can be dispersed in the solvent. So we can just spin coat or spray coat to grow the solar cell from the solution. So definitely if we can grow a solar cell from solution by chemical method, the price of the solar cell will be very less. These are the methods we are following. We are just synthesizing some nanoparticle based approach, or we can make some precursor. We put all the metal salt in some solvent, then we can make a thin film, and then after getting the thin film we can anneal them actually at 400 or 500 degrees centigrade temperature to grow the crystals, and from the crystals we can grow the solar cells. So this is the work. We actually spray the copper chloride, indium chloride and thiourea at 270 degrees centigrade on the moly substrate to grow the CIS layer, and then we selenize, means we are put in a tube furnace in presence of selenium powder. So selenium actually vaporizes at 500 degrees centigrade. So this type of big grains actually grow on this thin film. So we are making a solar cell with this one, and we are getting some efficiency around 5-6% efficiency from this solar cell. This is a ACM image of this solar cell, and now with this CIS, if you put the gallium, the band gap will be changed because the open circuit voltage of a solar cell, how much voltage you can generate, is depend on the band gap of the material. Because I told you that electrons and hole actually coming in the conduction band and valence band. So you are collecting the electron from the conduction band and hole from the valence band. So the energy of this electron and hole will be depend from their position. So it should be depend on the band gap. So if you put some gallium on this copper indium sulfoselenide solar cell, the band gap will increase. So definitely our VOC will increase. So we do the same recipe after incorporating the gallium, and we are getting the higher voltage. So device efficiency also increases. We are getting much more higher efficiency, but the short circuit current is little bit reduced. So still there is a scope. So I think we can make this type of solution process solar cell at least around in between 10 to 15% efficiency. Recently one paper I saw, it's reported around 12% efficiency by putting this type of solution based method. But the silicon solar cell, whatever people are getting from the single crystals, is giving around 23 to 24% efficiency. So though the efficiency for this type of solution based solar cell is little bit less, but still there is a big future. So we can make very cheap solar cells. So we can compromise a little bit with the efficiency because of the cheaper price. So another material for the CI copper indium sulfur selenide solar cell we did with the copper sulfide and indium sulfur selenide nanoparticle. These two nanoparticle we joined together to make the CIS solar cells. This is called the coalescence method. We try some copper sulfide and indium sulfide nanorod and we grow some solar cells. So there are lots of methods. You can grow different nanomaterial and you can make a solar cell by solution based method. And this is the another material is copper zinc tin sulfide, because if you see this copper indium gallium sulfide also we need indium and gallium. This indium and gallium is very expensive materials and we don't have lots of source in our earth because there are limited sources there. Lots of people are using the ITO because all the mobile phone, the transparent screen, all the television, the transparent screen, we are using the ITO, no? Indium tin oxide. So we are using the lots of indium there. So the indium price day by day is increasing too much. So that why people are thinking whether we can replace the indium by some common element like zinc and tin. So this type of materials are also used for making a solar cell. So instead of indium, we are using the copper chloride and zinc chloride, tin chloride and thiourea, and we just get a very clear solution in some organic solvent to methoxyethanol, and after spin coating and annealing in this type of similar 500 degrees centigrade, we can make a solar cell. And this type of solar cells, we are getting the efficiency around I think 10% efficiency is reported by this type of solution based solar cell. But the problem for these materials, so there are so many compounds there, no? Copper, zinc, tin, sulfide. So when you make this compound, there is a probability it can form copper sulfide, it can form zinc sulfide. So there is, if you see the phase diagram, only in the middle part it will form CZTS. So if you if you change the ratio between the copper, zinc and the tin source, it can give you some secondary phase, suppose zinc sulfide, copper sulfide and tin sulfide. So it's very tough to get a very pure phase CZTS. And also if you see the structure of this crystal structure, you can see the copper, this compound copper and the zinc, these two, blue and this copper is sitting very side by side. So they can change their place. If they can change their place, they will create some defect in the crystals. And whenever you have defect in the crystals, photogenerated charge carrier will be recombined. That's why this type of CZTS materials is very less efficiency, like 10% efficiency. So what we will do, we are actually checking whether we can replace the zinc with some other material. So copper and zinc replacement should be prohibited. We can block the copper to come to the zinc place. So we developed lots of material by replacing zinc like copper barium tin sulfide, copper manganese tin sulfide, copper iron tin sulfide, copper cadmium tin sulfide. We published one review article how we can replace the zinc with some different material to get some stable CZTS based solar cells. So some of our work on this type of alternative materials, this is the copper cadmium tin sulfide. We make a solar cells and we get some efficiency around 3%. And another type of solar cell from the solution is called known as the Dyesensitized solar cell. This is a very simple solar cell. We are just using some nanomaterial. So one of the electrode, we are putting some TiO2 nanoparticle, a very thick layer, like 40 micrometer thick TiO2 nanoparticle layer we are making, and on the top of the TiO2 nanoparticle, we are putting some organic dye. So whenever you give a light to the organic dye actually generating the electron hole pair, and this electron hole pair actually electron can be transferred to the TiO2 and TiO2 is transferred to the electrode. So normally the TiO2 layer we are putting on the IT or FTO substrate. So if IT or FTO is known as the collecting electron. So you can collect the electron from IT and FTO. Now the dye molecule, after giving the electron, we have to supply another electron to the dye molecule to regenerate to come back to the ground state. So that one we can use another electrode on the other side. We are normally using a platinum coated F2 electrode where platinum is work as a catalyst. So it's actually take this electron and give one redox couple. We want actually make an electrolyte by mixing the iodine and iodide. This iodine and iodide solution actually bring this electron and give it to dye molecule. So dye molecule come back to the ground state and again it can absorb the light and generate another electron. So this is the working principle of the dye-sensitized solar cell. So we need a two electrode. One is the FTO coated electron, another is the platinum coated electrode. And FTO coated electron we are putting the dye molecule, and in between this dye absorbed FTO coated electron and platinum coated electrode we are putting some liquid electrolyte, iodine iodide electrolyte, which is actually transporting the electron from one electrode to other electrode. These are the some of the picture, because the advantage of the DSSC, it can work very nicely in the low light intensity also. So in the inside the room you want to keep some solar cell, it will be work. And you can make it very colorful because we are using the dye molecule layer. So different colored dye molecule you can use to make your solar cell colorful. So these are some flower bus people are making. This is one building they put on the building wall with this type of dye-sensitized solar cells. This building, I think, in the Swiss Tech Convention Center in the EPL, Switzerland. So they put all the wall to get some energy, whatever the energy needed for this building from using the Dyesensitized solar cell. So now the problem of the Dyesensitized solar cell is the liquid electrolyte. So if you keep it for a long time in the direct sunlight, that liquid may evaporate. So you need a very nice sealant. You have to seal it very nicely that liquid should not evaporate out. So people are thinking how we can replace this liquid. So instead of putting the liquid, people are trying to put a solid state electrolyte who can transfer the electron or who can take the hole from the dye molecule. This is known as the solid state DSSC. So it's quite similar like the liquid DSSC, only thing is that you have to use the less thickness of the TiO2 particle and you can coat the dye molecule on the TiO2. Then instead of liquid, you are putting some P-type material. So this P-type material actually collecting the hole from the dye. So hole is going to the one electrode and electron is going to the other electrode. Now there is a recent development for this type of solid state Dyesensitized solar cell. So instead of dye molecule, people are actually trying to make some solar cell. The new material known as the perovskite material is a methyl ammonium lead iodide materials, and it's actually wonder material because it's giving very high efficiency. Normally for dye-sensitized solar cell, if you use the liquid electrolyte, it will give very less efficiency, around 12 to 13%, and if you use the solid electrolyte, efficiency is much more less, around 10%. But if you can make this type of solar cell instead of dye material, if you use this type of methyl ammonium lead iodide, it's also a colorful material. After absorbing light, it can generate the electron and hole, and it can give the electron to the TiO2, and people are getting more than 20% efficiency. I think now recently 24 point something efficiency reported for this material. So after the discovering of this material, there is a huge research thirst on making this type of solar cell. People are doing lots of experiment, and they found instead of TiO2, if they use the aluminum oxide, non-conducting material also, this device is working. So then they actually found that the TiO2 don't have that much role, that perovskite material itself can conduct the electron and hole to the two different electrodes. So instead of just like a thin film solar cell, they can use this perovskite material as a photoactive material, and they can put one N-type material and P-type material to collecting the electron and hole from this perovskite material. This is the how we can deposit the perovskite. Perovskite is the methyl ammonium lead iodide. So you can dissolve the methyl ammonium iodide in some organic solvent, and you can dissolve the lead iodide in the organic solvent. So you can mix these two solution, then you can spin coat to get a perovskite layer, or you can spin coat the methyl ammonium iodide layer, then you can spin coat the lead iodide layer, and if you heat them around 100 degrees centigrade, you can get a perovskite layer. So this is one of the advantage of forming the perovskite solar cell. You no need to go very high temperature. Low temperature itself can grow the perovskite solar cell. But another disadvantage is there that perovskite solar cell actually give very high efficiency when you are using the spiro as a hole transporting material. Spiro is very expensive, is an organic P-type material. So people are trying to replace the spiro, and we did some work whether carbon can replace the spiro. We try some carbon nanotube as a P-type material on the top of the methyl ammonium lead iodide. We make some solar cell and we are getting around 10% efficiency. And if you use this type of carbon nanotube, so we can make a freestanding film of carbon nanotube. It like just like a very thin paper-like stuff made up with the carbon nanotube or CNT. CNT is a nano form of carbon. It's highly conducting material and very strong material. So if you can put this type of hole conducting material, we can make our solar cell is flexible. So we try different flexible solar cell. We make a solar cell with the titanium substrate. We make a titanium substrate, deposit the perovskite on this titanium substrate, and then we put the CNT film to get the flexible solar cell. We take a titanium wire, then after depositing the perovskite, we wrap it with the carbon nanotube film to grow the wire-shaped perovskite solar cell. And recently, all this perovskite, we know the formula is the methyl ammonium lead iodide. So they have a lead. Lead is very toxic and poisonous material, and that way lots of research is going on whether we can make this type of solar cell free of lead. So we are developing a lot of lead-free material, perovskite material, and in our recent work we are focused on the lead-free perovskite material development. We are working on the silver bismuth sulfide, cesium bismuth iodide, cesium antimony iodide. We are developing lots of lead-free material, and we are making some photo detector with this type of material. And this is some recent work on the quantum dot, perovskite quantum dot. We have made very small size particles of this perovskite material, and if you give the UV light to this perovskite material, they actually emit the green light. So what is the advantage of this one? We actually take some UV LED. You can see these all the UV LED, and we cover this UV LED with this perovskite quantum dot. So we can change the UV light to the visible light. So if you can put this type of green emitting quantum dot and red emitting quantum dot and yellow emitting quantum dot, you can generate white light from the UV LEDs. These are the some different application of these perovskite materials. So there is a huge future for the perovskite solar cell. So I think in future we can make a perovskite solar cell very cheap and flexible, so it can replace the silicon solar cell. So I think whenever it will become very cheap, people can use easily the solar energy instead of the conventional grid energy. And this is the some company already started producing the perovskite solar cell, and they put some building integrated photovoltaic. So the surface of the glass, they put the solar cell on the building surface. This also, I think, from the Sol Technologies, they make this building where they put the perovskite solar cell. So I want to acknowledge all the funding agency from where I got the funding for continuing my research, the ACIRI DST and the DST TMD, and definitely I will acknowledge all my students who are working in the lab to produce all this result. Thank you. So recently, I think India achieved the 5th position for the solar power production. The country's solar installed capacity is now 53.997 gigawatt as per on 31st March 2020. So it's give a very good hope that I think near future will generate lots of solar power. So it's not very far that we can depend only on the solar power. We don't need to depend that much on the fossil fuel. Thank you. Your questions, so if you have any questions, you can put in chat box or you can directly ask me.
That was a very wonderful section from Dr. Sudip Kumar sir. Well, thank you for all the participants who have participated, and thank you so much.